Last time we discovered the method how to find the derivative of inverse functions. So just to recall this once more. Okay, so what we use in order to compute the derivative of an inverse function is the method of implicit differentiation. So we know that if we have an inverse function of some x is equal to y, that this is by definition equivalent to f of y is equal to x. So you can consider this equation as an implicit equation for the function y. And here you can use the method of implicit differentiation. Now, as I have explained, actually the method of implicit differentiation has some assumptions. Some assumptions must be satisfied. Now, the first assumption is if you have given an equation, so the first assumption is that you can solve actually for y. This is clear here in this context because we are talking about inverse functions. So, of course, you can solve here this equation is the first thing. The second thing is you have to make sure that the derivative exists in order to apply the method. And we saw last time, without proof, I told you that actually from this function f, you already see whether the inverse of the function is differentiable or not. Namely, if the function f is differentiable and has no horizontal tangents, then the inverse function is differentiable as well. So normally, if you have given an inverse function, we just go to the original function. We have already seen for most of the important functions that they are differentiable, and we can easily check whether they have horizontal tangents or not. And then we use the method of implicit differentiation. So the derivative here on the left-hand side is by the chain rule. The derivative of the function times of the outer function times the inner derivative is equal to 1. And then we solve for the derivative. So the derivative is 1 over f. So the derivative of the original function. And now we plug for y again the inverse function into the argument. So that's what we get for the derivative of the inverse function. Now, last time we saw already some examples. So we already used this kind of principle to find the inverse functions of trigonometric functions. And we also looked already at the inverse functions of exponential functions, which are logarithmic functions. So we saw that the derivative of a general logarithmic function with base x is equal to 1 over x ln a. So we see that in the special case where a is equal to the natural number, the derivative of the corresponding logarithmic function is getting in particular easy. Namely, you have here ln of x, and the derivative is just 1 over x, because this number here is equal to 1 by definition. Now, last time we also saw already an easy example. So some of you might have learned this already in high school, some not. So if you look at the function f of x is equal to ln of ln of ln of x. Okay, so you see that this function is defined if x is larger than e. Okay. If you compute the derivative, okay, so what you have to use here is the chain rule and this rule for the derivative here. So you see that if you look at the outist function ln, derivative is just 1 over. So you have ln of x. Now the next function, the derivative is 1 over ln of x. The last one, the derivative is 1 over x. So that's what you get for the derivative. And you see that the derivative actually would be defined on a larger domain, but of course doesn't make sense if x is between 1 and e. So of course this is just interesting for us if x is larger than e as well. Okay, so this is an easy example. Let's maybe just look at some more examples, because maybe some of you are not so familiar with the derivative of these kind of functions. Okay, so another easy example is like ln sine of x times the sine of ln of x. Okay, so now we combine already some of the rules we have learned or we have discussed. Namely, what we need is the product rule. So first the product rule. So we take the derivative of this function. And for this here, we need a chain rule. So this is 1 over, this is the cosine of x over sine of x times the sine of ln of x. So this was the derivative of this function times this function plus, now we just copy this function, so ln of sine of x. Okay, and the derivative of this function, we need again the chain rule, so it's the cosine of ln of x for the outer function, and for the inner function, you have an additional 1 over x. Okay, so this is quite easy. Of course, you can write here the cotangent of x for this function here, but you should get the principle how to do this. Now, if you have another example, for instance, if you want to compute the derivative of a general logarithmic function, let's say 10, and then you have x squared plus e to the x. Okay, so also this is easy now because we know that if we look at we have to use the chain rule. So if we look at the outest function, the derivative of this function is 1 over the rest, so 1 over x squared plus e to the x multiplied with the ln of 10. Okay, and then the derivative of the inner function multiplicated, so we can write it just in the numerator, so it's 2x plus e to the x. Okay, so also this is easy. You can do some more examples if you're not so familiar with derivatives of this function. Just to look at an example which is slightly more interesting would be this one. If you have the ln of the square root of 3u plus, doesn't matter, 2 over 3u minus 2. Okay, so of course one way is you just compute the derivative. So the derivative then of the ln would be 1 over this function, and then the derivative of the inner function. But you see, obviously, it's much easier if you do simplification first. Namely, you see this is 1/2 the ln of 3u plus 2 minus 1/2 ln of 3u minus 2. In this form, it's getting easier for this simple example. So sometimes it's good to do some simplification first before you compute the derivative. Okay, so you see that the derivative of this function is equal to, okay, so you have here 1 over, now 2. If you take the derivative of the ln, you get 3u plus 2 times the inner derivative, which is 3, minus, and the same here, with the only difference that you have 1 over 2, 3u minus 2, and here for the inner derivative you have again 3. Okay, so actually, it would be the same if you start immediately computing the derivative of this function, but more complicated because the derivative of this function is easy. It's just 1 over this function, but then the derivative of this function is more complicated. So you see here, by looking at this easy example, that it sometimes pays off to do simplification first and then to apply what we have learned so far in order to get the more easier way to compute the derivative. Of course, if you use immediately the chain rule for this function, you of course get the same answer, or you get an answer which is equivalent to this answer. Now, let's look at another example. Any questions? Any questions? No? So let's look at this function here, the ln of the absolute value of x. Now, in order to compute the derivative, we could here, one way is we differ two cases, x is larger than 0 and x is smaller than 0, because the function is different for those two cases. The function is obviously not defined for x is equal to 0, so we first look at case 1. Okay, x is larger than 0, so here the function is f of x is equal to ln of x. Okay, the derivative of this function is 1 over x, as we know. Now the second case would be the case where x is smaller than 0. So in this case, the function f of x looks a little bit different. It's ln of minus x. Now if you compute the derivative, okay, so actually you have to use the chain rule now. So the derivative of the outer function is 1 over the rest, which is minus x, times the derivative of the inner function, which is minus 1. So what you get is 1 over x. So actually you get the same as in the first case. So you see that, and this is an important result, so we memorize this. We see that the derivative of this function is 1 over x. Okay, wherever the function is defined. Okay, so of course if you plot the picture, you will see this as well. Or you at least get a feeling that this is true here, what we are doing. So how does the function look like? So our original function is this one. Okay, so this is the function y is equal to ln absolute value of x. And the answer, what we are getting is this here for the derivative. So this is the derivative. Okay, so you see that if you just look at the positive x, okay, then we know already that the derivative of ln of x is equal to 1 over x, which also makes perfect sense. You see, for instance, that the derivative is always positive. This corresponds to the fact that the function is increasing, and so on and so forth. And we had last time, in our in-class homework, we proved that the derivative of an even function is an odd function. And this already explains this part here. Because essentially, if you reflect the original function about the line y is equal to x, the only thing which changes is the sign of the derivative. This is what you have explained last time. This was one of the exercises last time in in-class homework, and this is essentially what you had to explain in part B of the exercise. Okay, you see, actually, it would be possible to get the derivative without computing, without dividing into two cases. Namely, you could write the original function as ln of the square root of x squared, okay, which is the same. And now you just use the chain rule, then you don't have to divide into those two cases. So you see that the derivative, okay, is 1 over the square root of x squared. So this is the outest function. Now we take the derivative of the square root, which is 1 over 2 times the square root of x. So this is the second function, and the last function, the most inner function is x squared, which has derivative 2x. And you see that from this here, you see that this is 2x over 2x squared, which is 1 over x as claimed. Okay, so here you do not have to divide into those two cases. X is larger than 0 and x is smaller than 0, so this is sometimes easier to apply. You see that if you slightly vary this function, so if you look at a function which is slightly different, namely you define it ln x plus some a if x is larger than 0, and ln of minus x plus some b if x is smaller than 0, then of course what you get is the same derivative. So the only thing you do is you shift this part of the function and you shift this part of the function. Maybe different, but this will not influence the slope of the tangent. So if you shift it up, of course the slope of the tangent in every point will remain the same. Okay. So we keep this in mind. This is an important result. Now, we will see the importance of this result in a few minutes. So we first look at another example. Okay, so we look at the function y is equal to the fourth root of x squared plus 1 over x squared minus 1. Now, this example does not have anything to do with logarithms, because there is no logarithmic function involved. And in order to compute the derivative, you can use the chain rule. So you have the outer function is the fourth root of something, which is 1 over 4, and then the something over 1 over 4 minus 1. And then you compute the derivative of the inner function, which is a rational function, which is also easy to do by using the quotient rule. But actually, there is a better way to do this. Namely, again, you first simplify the expression. Now, how to simplify something like this? You take the logarithm on both sides. This makes this expression obviously much easier, as we have seen before. So you see that the logarithm of y, you do not have to care about. Sometimes you have to be careful if you do something like this to take the logarithm on both sides, namely in cases where y is also negative for some x. But there is no danger here because you have the fourth root. Okay, so y will always be positive, so you can take the logarithm on both sides. And then you have here 1 over 4 ln of x squared plus 1 minus 1 over 4 ln of x squared minus 1. And now you see it's easy to compute. Here it's much easier to compute the derivative using the method of implicit differentiation. So if you compute the derivative here, what you get is, 1 over y times the inner derivative, which is equal to derivative of y is equal to, so sorry, this should be a 4, this is not y. Okay. And now the derivative on the right-hand side, which is 1 over 4x squared plus 1, and then the inner derivative of this function, which is 2x, minus, and you get the same. The only difference is that in the numerator, this is x squared minus 1, so you have 2x over 4x squared minus 1. Okay, so you see that what we want to have is the derivative. So you see that the derivative is equal to the original function y. You just plug in this expression here. Times this guy here. So times x over 2x squared plus 2 minus x over 2x squared minus 2. Okay, this is already the answer. So you see that in this case, okay, it's of course you could take the derivative of the original function, it's no problem, using the rules we have learned so far, but it's getting much easier if you take logarithms first and then use the method of implicit differentiation. This method is called logarithmic. Differentiation. Okay, so this is terminology, so you should memorize it. Logarithmic. The method of logarithmic differentiation means that you first take logarithms on both sides, and then you take the derivative of the resulting equation, which gives y as implicitly by using the method of implicit differentiation, and then you solve for the derivative. Okay, as I said, sometimes there is a problem here in using this method, namely in cases where one of those guys is, where both guys are negative, then you cannot use this method here. Okay, so for instance, it might be happen that for some x, the y is negative, not in this case, but for other functions. But you can use the same method, you just take the absolute value on both sides. Okay, and we saw that if you have the ln of absolute value of y, okay, the derivative is just the same, it's 1 over y. Okay, that's why I showed you this example that the derivative of the ln of the absolute value is 1 over of the ln of the absolute value of x is 1 over x. Okay, so maybe let's look at an example where we apply this, and this example is the proof of this rule here. X to the n is equal to n x to the n minus 1 now for all n real numbers. Okay. Sometimes it doesn't make sense here to talk about negative x. Sometimes it makes sense. If this doesn't matter, we get this rule here for all exponents which are real numbers. We haven't proved this yet. Okay. We have proved, just to remind you, okay, we have first proved for n is a positive integer, larger or equal than a positive integer, that this rule holds here by using the binomial theorem. This was the first step. The second step was, okay, for n is equal to 0, it's trivial. Then for negative n, we have used the quotient rule in order to prove this. And last time I have shown you how to use the method of implicit differentiation to get the case where n is a rational number. Okay? And now, in order to prove this rule for n is being any real number, what we use is this method here, the method of logarithmic differentiation. So just that you see how we prove this rule here. Okay, it's not so easy to prove. This is something you you have learned already in high school. I don't know whether you have learned it in this generality, so for every real number, but at least you have seen it for monomials, for power functions in high school. Okay, so how to prove this? Okay, now our function is y is equal to x to the n, and here in this case, okay, we might have, sometimes we have problems, okay, sometimes y might be negative, it depends on x and n, okay, so actually it's better to look at the absolute value of y, which is then the absolute value of x to the n. We have to exclude x is equal to 0 completely from our considerations, okay. Now, what we do is we use this method of logarithmic differentiation. So we take the logarithm on both sides. Ln of absolute value of y is equal to n times the ln of absolute value of x. Okay. Now we take the derivative on both sides using the method of implicit differentiation. So you see that for the left-hand side, you have the derivative of y over y is equal to n over x. Okay. We saw that the derivative of ln of absolute value of x is always 1 over x if you exclude x is equal to 0. And now we have, okay, solving for the derivative, we see that we get the claimed result. Okay, so this is the proof of the power rule. Of course, you might object because we haven't even proved this rule here. We haven't proved it for real numbers, okay? So you might object here. So you see there's still some work to do. But our problems are, as always, the same problems. Namely, I told you this in the first lecture, that it's not so easy to precisely define exponential functions. In particular, the case where the exponent is an irrational number was not so easy. We just looked at the graph and filled some holes. So this is not really a precise argument. But we will make up for this in maybe 1 month, so before Christmas. We will define precisely logarithmic functions and exponential functions, and then I have to do everything once more. Okay, I have to show you once more that the derivative of the ln of x is 1 over x and so on. Okay, so any questions to this? So keep this in mind that you have sometimes, if you use this method of logarithmic differentiation, sometimes you might run into problems if y is negative. So you have then actually to choose the absolute value. It's important that the method works, because otherwise you cannot take the logarithm on both sides. Okay, so now as explained in our textbook, we can handle all kinds of powers, a to the b, where a is might be a function of x, b might be a function of x. Also, both of them could be a function of x. So maybe let's look at one example just to see how to do this. So, for instance, if you are asked to find the derivative of this function here, okay, now the trick is to rewrite this in terms of exponential function of logarithms. So you see this is the square root of x ln of x. And now you can find the derivative. So dy over dx is equal to, so you have to use the chain rule here. Okay, so if you look at the e to the something is the outer function, the derivative is just the function itself. So you have x to the square root of x times the derivative of the inner function, which is 1 over 2 times the square root of x ln of x. So here you have to use the product rule for this function here, plus square root of x over x. Okay, so it's no problem for us now to compute the derivative of even such complicated functions. If you draw those functions, you will see that you find this in our textbook. So you find the graph in our textbook. You can use Maple in order to draw something like this. Now you start here at 1, so you have the original function looks like this here. Okay, and the derivative looks roughly like this here. Maybe it's okay. Okay, so of course everything is just defined if x is larger than 0. And you see, if you compare the properties, you see that, okay, at this point, the slope is equal to 0. The slope of the tangent is equal to 0, which is correct if you look at the derivative. You see that here the slope is negative, which you see here, and you see that here the slope is positive, which you see here. Actually, such relationships between the original function and the derivative we will discuss starting from next week here in chapter 4. And in order to really make precise, you see already, of course, it's quite easy to predict that if the derivative is positive, then the original function will be increasing and so on. So all those properties are easy to predict by looking at graphs. But starting from next week, we have to find a tool which gives us a better relation between the original function and the derivative in order to be able to prove results like if the derivative is larger than 0, then the original function is increasing without referring to any picture. But this is something we will do in chapter 4. In chapter 4, we will then apply what we have learned so far, so the rules for what we have learned so far concerning differentiation in order to figure out how the graph of a function looks like just by looking at properties, certain properties of the function. Okay, so this is one example. Another example would be, for instance, if you have a function which is implicitly given by this equation here. Okay, so for instance, this defines a function y is equal to y of x, and you are asked to find the derivative. Okay, then you use the let's call this. Sorry, let's call this. Okay, then here you have to use the method of implicit differentiation. It's not complicated. Now you just have to keep in mind y is a function of x. Okay, so if you take the derivative of the left-hand side, you write this as e to the y ln of x. So you compute the derivative here is equal to, and you write this as e to the x ln of y and compute the derivative here. Okay. Now here the derivative, you use the same method. So you get x to the y times the inner derivative, which is, okay, y is a function of x. So you have derivative of y ln x plus y over x is equal to, and here again the derivative of the outer function is the function itself. So what you get is y to the x, and the derivative of the inner function is ln y plus x, and the derivative of this function, which is the derivative of y over y. And now you solve this for the derivative of y. Okay, so you see that the derivative of y times x to the y ln of x minus y to the x minus 1 from this here times x is equal to, and the remaining part is y to the x ln of y minus y x to the y minus 1. Okay, so you see that the derivative of y is equal to y to the x ln y minus y x to the y minus 1 over x to the y ln of x minus y to the x minus 1 x. Okay, so it's not complicated. It's just a kind of mental exercise not to get mixed up with x and y depends on x. Okay. Actually, what we can do now is to find the expression for the first time for the number e, which we have defined quite awkwardly at the beginning of this lecture as the tangent. So the natural number e, just to remind you, originally we have defined it as the exponent of the exponential function, which has the property that at x is equal to 0, the tangent has slope equal to 1. Okay, so you see already here, this is a very awkward definition, okay, because I have to use 2 minutes to tell you this definition. Okay, so or to write it differently, okay, we defined this number here. We defined this number such that the limit e to the h minus 1 over h as h tends to 0 is equal to 1. So we define this number here, e, like this here. Okay, this is not a very good way to, for instance, if you're interested computing digits of e, okay, this would be not a very good way, convenient way to compute digits. Okay, of course you can use like Maple. You try to find the basis, okay, such that if you check at 0, the slope of the tangent is equal to 1, roughly. Okay. And like this, you can get approximations for the number e, but it's not a good method. So we need better expressions for the number e. Now we can derive one, namely e is a limit. Okay, so we look at the function f of x is equal to ln of x. Okay, so we saw already that the derivative of this function is equal to 1 over x. So in particular, the derivative at 1 is equal to 1. This is quite helpful because we can now plug in the definition of the derivative. So 1 is equal to the limit as x tends to 0. Now, f of 1 plus x minus f of 1 over x. Okay, so you see this is the limit. X tends to 0. Okay, so if you plug this in here, f of 1 is equal to 0. This is the ln of 1 plus x, and 1 over x we can take here in the exponent. Okay, so you get that this limit here is equal to 1. This is already quite helpful. Now you see that, okay, if you start with e, you can write e as e to the 1, and you just plug in what we have proved so far. So 1 is equal to the limit x tends to 0, 1 plus x to the 1 over x. And now we know that this function, the exponential function, is continuous, so we can take out the limit. So we have this is equal to the limit as x tends to 0 of e, sorry, here's the ln, of e to the ln, which is 1 plus x to the 1 over x. Okay, so we have here now a formula which gives us at least theoretical a way to compute e. Namely, if you compute the limit here, if you plug in here values for x which are small, you will approximate e. But this is not a good method, because if you really try to do this from a certain extent on, you will get 1 as the answer if you just use your calculator. Because if you make x too small, okay, then the number 1 plus x for the calculator will be equal to 1, and what you get is 1. So actually, this is not a good method to compute e. We will, next semester, we will learn a much better method, which gives you easily E up to many digits. I think Euler himself computed already quite a lot of digits, maybe 26 or even more. Of course, he didn't use this method here because this method would be too awkward to compute approximations for the number E here. You can see that you can also rewrite this, which is done in our textbook as well, in this form here. Maybe you have seen this form already in high school, because if you look at 1 over n here, if n tends to infinity, then this here actually tends to 0. Okay, so this is just the same here, just by a change of variable. So you see that E can be represented as the limit n tends to infinity 1 plus 1 over n to the n. Okay, so you might have seen this in high school. This is already this already gives a first possibility how to compute E, but as I said, as I have explained, not a very good one. This is not a very good one. A very good method to compute E. And we see already from here that if you are interested in a limit which is pretty similar, namely 1 plus x over n to the n, okay, so you can now handle, where x is any constant, you can handle this limit as well, namely you write here n over x to the x, okay, and now you see that because the function the function a to the x is, or the function the function x to the n, where n is a power, is continuous, so you can write this here as the limit as n tends to infinity, 1 plus x over n, n to the x, and this here tends by the same argument to e, so you get e to the x. So you see that this would be a different method. Maybe I just write this once more. This would be a method to compute the exponential function e to the x for some given x here. So if you have x, for instance, square root of 5, you can plug in here square root of 5, and you try to approximate this limit in order to get an approximation for the original function. Moreover, this would be also a method in order to you could reverse now everything logically, and you could say, okay, we define the function e to the x like this here. Some textbooks work like this, but normally textbooks for mathematics students, not for engineer students. In mathematics, it's quite common sometimes to define the number e to the x just by this limit relation here. But you see, if you make such a definition, it would be much harder to, for instance, figure out that this function e to the x is, for instance, increasing. Easy properties are already complicated to prove by such a definition. And of course, it would be much more complicated to prove that the derivative of e to the x is e to the x. Even that the function is differentiable, it would not be easy to prove if you define it by such a limit relation. Okay. Now, this is, I think, one of the examples in our textbook. Now, we look at the third class of inverse functions, namely inverse functions to hyperbolic functions. So we saw already how to compute the derivative of inverse functions of trigonometric functions. We saw how to compute the inverse functions, the derivative of the inverse functions of exponential functions. Now another class of functions which we have discussed in the assignments are the hyperbolic functions. For instance, the hyperbolic sine, which is defined as e to the x minus e to the minus x, half the hyperbolic cosine, which is defined as e to the x plus e to the minus x, half. And let's also consider the hyperbolic tangent, which is defined just as the quotient of the hyperbolic sine over the hyperbolic cosine. Okay, in the first assignment, you were already asked to plot graphs of those functions. If you plot the graph of this function here, this is something we haven't seen yet. I tell you how the graph looks like. So the graph looks roughly like this here. Okay, so this is this function here, the hyperbolic tangent, where you have two horizontal asymptotes. You see, if you plug in the definition, what you get here is e to the x minus e to the minus x over e to the x plus e to the minus x. As x tends to infinity, this tends to 1. Okay, and as x tends to minus infinity, this tends to minus 1. So this is the graph here of the hyperbolic tangent. You see already here also 1 to 1. So you can define inverse functions of those functions. For the sine, it's no problem, also 1 to 1 everywhere. For the cosine, you have to restrict the domain. And one possibility to restrict the domain is for x larger or equal than 0. Maybe because I've never mentioned why are we interested in such functions, why are those functions important in applications. If you consider the following problem, you take a rope, you keep it like this, you fix it like this, a rope. Okay, so it will take some form. You know what I'm talking about. You take a rope, you fix it like this here. It will take a form. Okay. If you ask a high school student, okay, what do you guess? Which curve is described by the form? Every high school student will tell you x squared, which is not true. It can be proved. It's exactly this one. Okay. So under some, of course, this is a model. Okay. So under some assumptions, you can prove that if you fix a rope, okay, like this, then it will take the form of the cosine of the hyperbolic cosine. This is important in applications because, for instance, if you consider those electricity cables, okay, you fix them between two poles, okay, and the form which is taken, which they take, is the hyperbolic cosine. So this is important for applications. That's why those functions are important in applications. Now, in the assignments, you were already asked to find expressions for the inverse functions. So you have already proved in the assignment that, for instance, the inverse sine of x is equal to the ln of x plus the square root of x squared plus 1. Now, this is the inverse sine, hyperbolic sine. Now the inverse hyperbolic cosine, there is a similar formula. Here you have to decide, okay, how you restrict the domain. The standard way to restrict the domain is consider x is larger or equal than 1. So you have, for the cosine, the standard way to restrict the domain is x is larger or equal than 0. Okay. So you look at the right part of the graph, and then you get for this. You can, like this, then the function gets 1 to 1. You can define the inverse function, and the inverse function you have proved in the assignments that you can use this expression here. So this is, you need the restriction that that x is larger or equal than 1. And for the hyperbolic tangent, you can do something similar. And then you get an expression which is 1/2 ln 1 plus x over 1 minus x. And you see that the domain of the inverse function of the hyperbolic tangent is minus 1 to 1. So if x is... Okay. This actually is not surprising because the original functions are defined via exponential functions, so it's not surprising that the inverse functions can be expressed in terms of the natural logarithm. And in order to compute now the derivatives of the inverse functions, we have two different ways to do this. One way is to use implicit differentiation, as we have done for trigonometric functions, and the other way is just to take the derivative here of those expressions. So let's look at the derivative of the inverse hyperbolic sine function. Okay, so you can use this expression here. So you see by the chain rule, this is 1 over x plus square root of x squared plus 1 for the outer derivative. And for the inner derivative, write it here, 1 plus, and here you have to use the chain rule again. So it's x over the square root of x squared plus 1. Okay, so you see that what you get is 1 over square root of 1 plus x squared. Okay, so this is different to the trigonometric functions where we have seen that the derivative of the inverse sine function is 1 over the square root of 1 minus x squared. So for the if you delete the h, then you would have here minus. Now, this is one way to compute the derivative of the inverse hyperbolic sine function. Another way is to use implicit differentiation. So maybe let's check that the answer is the same. You can express the inverse hyperbolic sine function in terms of the hyperbolic sine function. Now you take here derivatives on both sides. We know that the derivative of the hyperbolic sine is the hyperbolic cosine. So you have the hyperbolic cosine of y times the inner derivative, which is the derivative of y, is equal to 1. Okay, and we remember that the hyperbolic cosine square minus the hyperbolic sine square is equal to 1. Okay, so we see from this relation that the hyperbolic cosine of y is equal to 1 plus the hyperbolic sine of y square, the square root. You can forget about the negative root. Actually, you have 2 here, plus minus. So maybe just to make this precise here, you have here 2 roots, plus minus. But you can forget about the negative one, because the hyperbolic cosine is always positive. Okay, and now, if you use this, if you plug this in, and for y you plug in the original function, you see what you get is the same expression. So the derivative is equal to 1 over square root of 1 plus x squared. Okay. And similar for the other inverse hyperbolic functions. So the derivative of the inverse hyperbolic cosine is 1 over the square root of x squared minus 1. And the derivative of the inverse hyperbolic tangent is 1 over 1 minus x squared. So all those signs are a little bit different compared to trigonometric functions. But the expressions more or less are the same, just some signs are different. Of course, you do not have to memorize all those formulas. You can look them up if you need them. Maybe because I have never explained as well why those functions are called hyperbolic functions. The reason for this, you can see here. Okay, namely, if you compute for some y the pair hyperbolic cosine of y and hyperbolic sine of y, this point will lie on the hyperbola. That's why these functions are called hyperbolic functions. And this is similar to trigonometric functions, where if you compute for some x, sine of x and cosine of x, this pair, this point is on the circle, on the unit circle. So that's the reason. So this relation is actually the reason why those functions are called hyperbolic functions. And we saw already that they have many similarities, many relationships to trigonometric functions. For instance, you can try to prove on your own that the hyperbolic sine of x plus y is equal to the hyperbolic sine of x times the hyperbolic sine of the hyperbolic cosine of y plus the hyperbolic cosine of x times the hyperbolic sine of y. So you have exactly the same formula as for trigonometric functions, and you can also prove similar formulas for like the hyperbolic cosine of x plus y and so on and so forth. So you have many relationships, but many similarities, but there are still some small, tiny differences where you have to be careful. If not, then we go on to the next section, which is section 3.10 in our textbook, which discusses related rates. So this you can see this as an application of yet another application of the method of implicit differentiation. So what we are interested in here is to compute the rate of change of a certain quantity, and normally we can express the quantity in terms of other quantities. If we are able to do this, we can take the derivative from both sides of such an equation, and we will get a relation between the related rate which we want to find and the rate of other quantities. And sometimes other quantities are more easy to measure. So, for instance, if you in our textbook you find the example where you pump air into a balloon. Okay, as you pump air into the balloon, the radius will change. And for instance, we are interested in the rate of change of the radius of the balloon, so how the radius changes over the time. Now, this is something which is not so easy to measure, but what is certainly easy to measure is how much air you pump into the balloon. For instance, every minute, how much cubic centimeter air you pump into the balloon. This is easy to measure. So you see that you have the rate. Normally what you can easily measure is the rate of change of the volume with respect to the time. And what you have to find is the rate of change of the radius with respect to the time. But we all know that there is a relationship between the volume and the radius. So we actually start from this relationship. So you know that V is equal to 4/3 times pi times r to the cube. So this is how you compute the volume if you know the radius. And if you now want to know the rate of change of the volume of r, so what you use here is just implicit differentiation. You assume that all the quantities now depend on the time, change with the time. So as you blow air into the balloon, the radius is changing with the time, and the volume is changing with the time as well. So you see that dV over dt is equal to, and here we have 4 times pi times r squared times dr over dt. Okay, and now if you, for instance, this quantity normally you know, because you know how much air is going into the balloon, for instance, every minute. You can measure this easily. And if you're now interested in, okay, what is the rate of change of the radius when the balloon has already reached a certain radius, you can use this equation to compute this quantity. Now, those are the so-called related rates problems. So you have to find the rate of change of some quantity, and normally you cannot measure this rate of change easily, but you can measure the rate of change of other quantities more easily, and you have a relationship between all those quantities. Okay, so maybe let's just do some examples to see what this is about. So there is another example in our textbook. I just used the same example. Okay, so what we have is a ladder. Now, in our textbook, because this is an American textbook, they are using feet. I'm not so used to this measure, so I use meter instead of it, the metric system. So let's say the ladder has length 1 meter and rests against the wall. So maybe let's already draw a picture. Okay, so we have this ladder. Okay, which has height 1 meter and rests against the wall. Now, so let's maybe this distance, let's denote it by x. This distance, let's denote it by y. Now what you know is that the ladder slides away from the bottom of the wall at the rate of, let's change this to 1 decimeter per second. So you know that here the ladder slides away at the bottom, okay, at a certain velocity, and we are interested to know, okay, what is the change of y with respect to the time when the distance here is 6 decimeter. Okay, so what is the rate of change of y if x is equal to 6 decimeter. And what we have given is dx over dt, which is 1 decimeter per second. Okay, so this is not this is not a complicated example. Now I'm not writing more details, so please read it. If you do not understand my explanation, I just try to save a little bit time. If I write out the whole problem setting, it would take too much time. So read it in our textbook. It's the same example as in the textbook. So once more, we have a ladder with height 1 meter, which rests against the wall. So you have a wall here. Now, what you know is that the ladder is sliding away at the bottom at a certain velocity. And what you are asked to find is the rate at which the ladder, at which the top slides down if x is equal to 6 decimeter. Okay, so also here you see that the only thing you have to do is you have to find the relation between the quantities in question. Then you take derivatives, and then you plug in the information you have. Okay, but to find the relation here between the involved quantities is very easy, because you know that x squared plus y squared is equal to 1. Now, x and y both depends on the time. Okay, so you can take the derivative here by using the method of implicit differentiation. So 2x dx over dt plus 2y dy over dt is equal to 0. Now, what we have is dx over dt. What we have to find is dy over dt. And we have another information, which is x is equal to 6 decimeter. So you see from at this position, so if x is equal to 6 decimeter, then y, by using the original equation, is equal to 4 decimeter. Okay, so this is the only thing you have to plug in. So in order to find the rate of change of y with respect to t, we solve this equation for dy over dt. And what you get then is minus x over y dx over dt. Now you plug everything in, so we have everything already in the correct units. So it's minus 6 over 4, and dx over dt is 1. So this is the rate of change of y here. Of course, it's negative because it's getting smaller as x is getting larger. Okay. You see here actually something interesting, namely if y is very small, okay, so you see if y is very small here, you see that this quantity is getting very large, okay. So for instance, if the velocity with which the ladder slides away here is fixed, okay, and you have y is very small, okay, then what you get is here something very large. So in particular, you can easily find small enough y such that this here is larger than speed of light, which is something which is not possible, as you know, from physics. So you can think a little bit about it. This is not important for this class because we are not talking about physics, but it's still interesting because it seems to be a very easy model, but it doesn't work if y is very small, because in this case, the answer which you get obviously is wrong. Cannot happen in physics. Okay, I'm not working in physics, so you might understand physics much better than I do. So maybe most of you know what the problem here is. Okay, so how much time do we have? So let's maybe look at some examples. For instance, let's look at example 29 in our textbook. Here we have two resistors. This is section 3.10, example 29. So you have two resistors which are connected in parallel. So you have something like this here. Okay, so you know that, so this is here resistor 1, R1, and this resistor 2, R2, and you know that there is a relationship between, if you want to compute the resistance of the whole circuit, you know you can do this by the formula 1 over R is equal to 1 over R1 plus 1 over R2. Okay, now, if you read this example carefully, what is given is, both of those resistors are changing. The value of them is changing over the time. So what you have for the first one is dR1 over dt is equal to 0.3 ohms per second. This is for the first one. And for the second one, the constant change over the time is 0.2 ohms per second. Okay, and you are asked to find what is the change of R if R1 is equal to 80 and R2 is equal to 100 ohm. Okay, you see, if you want to solve such an example, normally the first thing you do is you read carefully the problem setting. Then you try, in most of the examples, it pays off to first to plot a picture. Once you plot a picture, you have to introduce notation. So for this example, I think if I remember correctly, the notation is already introduced in the textbook. You have to figure out, okay, what is known, what is unknown. You relate those quantities by something which is normally something which arises from mathematics, or here in this context, which arises from physics. Then you take the derivative by using the method of implicit differentiation, because you assume that everything here depends on the time, and then you just plug in what you solve for the quantity you want to find, and you plug in everything. So in this case, you have to compute first for the case where R1 is equal to 80 ohm and R2 is equal to 100 ohm. You use this formula in order to compute the total resistance, which is 1 over 80 plus 1 over 100. I have written this down, then I don't have to do this these very easy simplifications on my own. So 0 over 400. Okay, so R is equal to 400 over 9. And now you take, so everything depends on the time here. So you take the derivatives on both sides. So the derivative. Here you have to use the chain rule. So you see minus 1 over R squared. The derivative of R with respect to t is equal to, and you have the same here. So minus 1 over R1. The derivative square, the derivative of R1 with respect to t plus minus 1 over R2 squared, the derivative of R2 over t. Now, all those quantities we have, so this is 80, this is 100, the R here is given here, and we also have this quantity and this quantity, so we just solve for the unknown rate of change. And for this one, we have R squared times 1 over R1 squared dR1 over dt plus 1 over R2 squared dR2 over dt. Okay, and then we plug everything in, and we get the solution 107 over 810, which is 0.132 ohms per second. So this is the answer. Okay, so this is another easy example. Now maybe let's choose another one. Let's choose a final one. Let's choose 38. This example maybe is slightly more interesting. Okay, so first let's read the problem setting. So you have a runner which sprints around a circular track of some radius, which is 100 meter, at a constant speed, which is given 2 meter per second. Also, the runner's friend is on the track. He's standing 200 meter from the center of the track. And now the question is, how fast is the distance between them changing if the distance is equal to 200 meter? I don't know whether it was enough time, but I'm just explaining you the idea how to do it, or you want to have a little bit more time. So, okay, so actually what you do first is to draw a picture. So you have this circular track here. Okay, and we have our runner which is running around here. So for instance, let's assume he's at this position here. Okay, we know that the radius is 100 meter. And we know that the friend is standing 200 meters away from the center. So we have here, okay, so maybe the friend is standing here. Okay. So this is the position here of the sprinter. This is the position of the friend here. We have here 200 meters. Okay, now what we are interested in is this distance here. Okay, so let's introduce a name for this distance. So this distance, let's say it's called L. Okay, and we are interested in the rate of change of L over the time. Now, so this is the quantity we have to find at a certain point, namely when the distance between them is 200 meter. Okay, so at a certain point, but you know what I mean. So this is what we have to find. Now, you see, if you do such an example, first draw a picture, then introduce names for the quantities in question. So here we have an L. Another quantity which is seemingly important is this angle theta here. Also, what will become important is the length here of this arc, okay, which we call d. Okay, so we have introduced now some notation. Now, if you look at the geometric situation, you can easily find relation between L and some of the other quantities. Namely, you know that L square is equal to 100 square plus 200 square minus twice 100 times 200 times the cosine of theta. Okay, so this is a relation you know from high school. If you have a triangle and you want to find the length, this is something like the Pythagoras theorem, but for a more general situation where the angle here is not a right angle. Now you see this still depends. So we can. Okay. Now you see this still depends on theta, but actually we have given something different. Namely, we have given that the speed at which the sprinter is running is how much? 7 meters per second. So we know that dt over dt is equal to 7 meters per second. This is something which we know as well. Now, okay, so here you have L square is equal to, now let's compute this. So 15,000 minus 40,000 cosine of theta. Now so everything depends on the time. So we take the derivative. So you have 2L dL over dt is equal to minus, so you have 40,000 sine of theta d theta over dt. What we still need is the d theta over dt. This is the first thing we need. The second thing we need is if L is 200 meter, we need to find out, okay, what is the theta? Okay, so those two quantities we still have to find. Now, as for this one, this is quite easy because we know that d is equal to 100 times theta. Okay, so you see that the derivative is equal to 100 d theta over dt. So you see that d theta over dt is equal to 7 over 100. That's the first thing. Now, we know L is equal to 200. So for this point, we have to find the rate of change. So we have to find theta for this situation. So maybe I just write this, what I just have done here. Okay, so what is the sine of theta if L is equal to 400? To 200, sorry. So in this case, you have here 40,000 is equal to 50,000 minus 40,000 cosine of theta. So you can see it like cosine of theta. So you see that this gives that the cosine of theta is equal to 1 over 4. Okay, so the sine of theta is equal to the square root of 1 minus the cosine square. Actually, minus, okay, but we do not really know whether so actually we can take into account here plus minus. This gives us then two solutions, but the only effect of this plus minus, okay, to the dl over dt is that it's either plus or minus. But actually, we do not know whether the distance here is increasing or decreasing because this depends in which direction the sprinter is running. And if you look at the exercise, there is no indication in which direction the sprinter is running, so we do not have to care about this. So actually, we could forget here about the sign. From here, you see, okay, that the sine of theta is equal to, so you plug this in here. Then what you get is 16, 15, square root of 15. Okay, and now you can plug everything in and just compute the quantity you want to compute. So maybe I also write this here. So the sine of theta is the square root of 15 over 4. Actually, if I'm very precise, I have to use here plus minus. Okay, and now I have to solve for dl over dt, and I get the quantity which I want to have. So dl over dt is equal to, okay, so I have here 7 over 100 over 100. I have here 20,000 if I divide by 2. The L is 1 over 200, and I have the sine of theta, which is the square root of 15 over 4, and I have also here plus minus, so you see what you get is plus minus 7 square root of 15 over 4, which is plus minus 6.78 meters per second. Okay, so when L is 200, okay, the rate of change or the speed of the sprinter is equal to 6.78 meters per second. Sorry, not the speed of the sprinter, but the rate of change at which the distance between the friend and the sprinter is changing. And as I have explained, you see you have a sign here, plus minus, but this sign is not important for us because you do not know in which direction the sprinter is running. You also see, okay, here how to solve such an example. So if you couldn't solve, if you couldn't set it up in the 5 minutes I gave you, you just have to do this in a systematic sense. So first you start by drawing a picture. Okay, then you introduce names for all the quantities in question, which are important. Then you identify the quantity which you want to find. You identify the quantity, all the quantities which are given. You set up a relation between all the quantities. Sometimes you can eliminate some of the quantities. We haven't seen here an example, but you have an example in our textbook where sometimes you can eliminate one of the quantities if this equation depends on more quantities. Then you use the method of implicit differentiation to compute the derivative on both sides of the equation involving all the quantities, and you solve for the rate of change you want to find, and you plug everything in and compute the final solution. So actually those examples are not very complicated, and we will do more of them in the assignments. You just have to be careful not to plug in. Of course, you are not allowed here at this stage to plug in already the cosine of theta is equal to 1/2. Okay, if you plug this in, then you will get 0, and this obviously is incorrect. Here in this example, okay, is a trivial remark because there is no danger. But if you have more quantity, if this equation involves more quantities, okay, sometimes you might get mixed up and plug in some of the quantities too early. But this, of course, will not give you the right answer, because if you plug in here the cosine of theta is equal to 1/4, you just have a constant here whose derivative is equal to 0.